In this section, we will introduce vectors, and we'll begin with the definition of a vector. So let's begin with the definition of the vector. A vector is a quantity drawn as a line segment with an arrowhead at one end. The vector has an initial point where it begins, and it has a terminal point where the vector ends. A vector is defined by its magnitude, which is simply the length of the line, and its direction, which is indicated by an arrowhead at the terminal point. A vector is what we call a directed line segment. Now here's an example. Many quantities in physics can be represented by vectors. In this example, we're looking at the velocity of an aircraft, and that velocity can be represented by an arrow that points in the direction that the airplane is flying. It looks like this airplane is flying west. The length of the arrow represents its speed. So 425 miles per hour is being represented by the length of this vector. If the aircraft speeds up, then we might lengthen this vector. If the aircraft changes direction, then we would introduce an arrow in that new direction. Now in this example, we see another vector. It looks like going about 40 miles per hour, and it's drawn 45 degrees. It looks like southwest of what that airplane was going. That might be a wind that is coming in and blowing in that direction. And what we can do with these vectors is use that information to see how that might affect the path of, not only the path, but the path and the speed of the airplane. Some more properties of vectors are that any vector can be written as what we call a position vector, which means that it has its initial point at the origin, 0, 0, and a terminal point at some point. We'll call that A, B. In the diagram that you see, in the graph that you see, vector AB is an example of a position vector, and that is because vector AB has as its initial point the origin, and then its ending, its terminal point is at some point A, B. Vector CD is not a position vector because vector CD in the picture is not beginning at the origin. However, vector CD can be written as a position vector by thinking about the change in the x and the y coordinates, where vector CD written as a position vector would equal the difference in the two x values and the difference in the two y values. Now, a thing about notation, let's just talk about notation for a second. Notice that when we talk about a vector, we're going to always put a little arrow above that vector. That indicates that it is a vector. If it's a position vector, then we see these sort of brackets that are on the side. They're not parentheses, they're not brackets, they look like V's that are put on their side. And that indicates to the reader that we have a position vector, meaning that the initial point is at 0, 0. So let's try an example. Show that vector V with initial point at -1, 2. Let me go ahead and put that on the graph. So I'm going to start at the origin and go to the left 1, and I'm going to go up 2, and terminal point at 4, 5. So 4, 5 is about right there. So that, if I connect those two, notice I'm going to put the arrowhead at the terminal point. That's vector V. Not a position vector, right? Because it's not starting at the origin. Show that vector V is equal to vector U. Let me do vector U in a different color. Vector U has an initial point at 1, -1, so it's down there in the fourth quadrant. And it has a terminal point at 6, 2. 6, 2. So I'm going to connect those, and that is vector U. All right, so they're not position vectors again because they don't have their initial point at 0, 0. All right, so how am I going to do this? To show that they're equal, what I might want to do is find out what their position vectors are. So I'm going to use the property that we talked about earlier. I'm going to say that vector v is equal to, I'm going to do position vector notation here, put that v that's on its side, and I'm going to start by subtracting the x values. Now, I have an x value of 4 and I have an x value of -1. This is very specific. Subtraction is not commutative, so the order here makes a difference. I'm going to start with the x value of my terminal point, which in this case is 4. I could call that my x sub 2. And I'm going to subtract from that the x value of the initial point, which I'll call x sub 1. So I'm going to have 4 minus -1, comma. Now I'm going to subtract the y values, and I'm going to also start with the y value of the terminal point, which is 5, and I'm going to subtract 2 from that. And I'm going to close that off with the v. All right, so what does that equal? 4 minus -1 is 5, and 5 minus 2 is 3. All right, so what that tells me is that vector v is equivalent to a position vector of 5, 3. The position vector means that it's going to start at the origin, and then it's going to go to the right 5, and it's going to go up 3. So if I connect that, sort of go through that U, does it look like that position vector is the same? Does this red vector look as though it's the same as vector v? And I would say, just eyeballing it, it does look like it is. Now, it has moved, but the length of the vector and the direction of the vector has not changed. Just imagine picking up that blue vector v and shifting it down to where the position vector is. Now, let's see if vector u has that same position vector. If it does, then that means that these two vectors are equal. All right, so vector u. Vector u is going to be, I'm going to put that position vector notation, and I'm going to subtract my x's. So I'm going to have 6 minus 1, comma, 2 minus -1. Oops, I put a parenthesis there, didn't I? All right, so don't do that. Let's change that to the v on its side. All right, so 6 minus 1 is 5, and 2 minus -1 is 3. And sure enough, these both represent the same position vector, and therefore they are equal.